So I'd like to thank the organizers for the invitation and the opportunity to talk here. And so my talk is around free entropy, so it's mostly a background talk about free entropy, some connections, something about some open questions, and So free entropy appears in the free probability framework. I'm taking here the simplest situation, that is the tracial situation. So I'm having the von Neumann algebra with a tracial state, yeah, M and tau, a tracial state. So you can figure out that M acts on a Hilbert space, yeah, and the tracial state comes from a vector. So it's vector written as a vector state. The random variables of the theory are elements of the von Neumann algebra. The distributions of the random variables are given by moments. So you take products of stuff like that and you look at their expectation tau of such products. Well, these are the non-commutative moments. And then there is a notion of free independence, which I'm not going to write down what it is, but I hope you've heard about it and know about it. So it is a notion, very non-commutative, which in this framework will replace the usual independence. You know, the usual independence models tensor products. This one models, we may say, free products. And then the theory, part of it, has developed based on this analogy, that is, it's a parallel between basic classical probability and this free probability. So you take some basic notion in classical probability and hope you can find free probability analog of this notion. And thus far there have been quite a lot of things which have free probability analogs. It goes really quite far, as I might say, unexpectedly far. And what we have to discuss today is what happens with the analog of Shannon's continuous entropy. It's also called differential entropy, Shannon's differential entropy or continuous entropy. So you have, classically, you have n real valued random variables. They have a joint distribution which is absolutely continuous with respect to Lebesgue measure on Rn. The density is P of T1, Tn, d lambda, lambda for Lebesgue measure. And then the Shannon differential entropy is this formula, which is like the discrete one, but it's an integral. It's become continuous, so it's minus the integral over Rn, P of T1 Tn, logarithm of P of T1 Tn dt1 dtn. And the corresponding quantity should be something which we're going to denote chi. Yeah, chi looks a bit like h. Yeah? If you know a bit of Greek, huh? Whatever. And f1, fn will be x1, xn. Here, self-adjoint elements of the von Neumann algebra. And we want a quantity which should be similar to h. And there are two ways to get to such quantities. One is the microstates approach. It's based on microstates. I'll say a little more why we're talking about microstates. And then there is the contrary, with the one which is not based on microstates, and the one which is not based on microstates enjoys already two names. Either it's called microstate free entropy, or it's called non-microstates free entropy, but it is some contrary to microstates. So the microstates one goes like that. We're having this n tuple of non-commutative random variables, so this n tuple of self-adjoint elements in the von Neumann algebra with the tracial states. And then we're having microstates with a certain degree of approximation. So it's microstates will be k by k self-adjoint matrices, yeah, in mk, yeah. So you have x1, xn, and then you have an n tuple of matrices, k by k matrices. And the assumption is that if you look at the moments, the non-commutative moments up to degree m, the moments are taken here for the matrices with respect to the normalized trace. When they are within epsilon of the moment of xi1, x1, xn, yeah? So out of xn, xn, x1, xn, you have tau of xi1, xip. Out of a1, an, you have this normalized trace of a1, ap. And then you require that these moments should be within epsilon of each other. And then the next step is to take some kind of normalized limit of the logarithm of volume of the microstates. Yeah. So you have logarithm of volume of gamma of this microstates space, and you do lots of normalizations, which so you do k minus 2 of the logarithm of this. You make also this additive adjustment, n over 2 logarithm of k, and then you take infimum over epsilon positive, infimum m over n, and you put limit superior so that you have a well-defined quantity. I mean, it would be nicer if you could put there a limit, but it's only lim sup, because you don't know that the limit will necessarily exist all the time. So it's in any case a normalized thing of the logarithm of the volume of the microstates, and that's chi of x1, xn. And what one gets in the case n equal 1, so if one has just one variable. If one has one variable, then the quantity should depend on the distribution. So it should depend on the moments of x. We're having one non-commutative variable x. This non-commutative variable is self-adjoint. So then these moments, the traces of x to the n, are actually the moments of some probability measure on R. If you want the probability measure, you can say also that it is the trace of the spectral measure of x. And what you get is that this entropy is an adjusted minus. So you see here you have this double integral logarithm of absolute value s minus t d mu s d mu t. This is, because the sign is plus and not minus, this is minus the logarithmic energy of the distribution of d mu s d mu t. So it is a slightly adjusted minus logarithmic energy of the distribution. That's what's happening for n equal 1. And all this microstates approach is inspired by the Boltzmann formula for entropy. It says entropy is proportional to the logarithm of the probability of a state. You have states in some system, and then you have microstates which approximate, and then you, with the probability, the Wahrscheinlichkeit W of the state is roughly something proportional to the number of corresponding microstates. And that's Boltzmann's famous formula, which has inspired so many things. And one should be careful about one thing. If one has this x1, xn, these non-commutative random variables, so these are self-adjoint elements in the von Neumann algebra M, and then one may ask, if I set the approximation quite high, yeah, you see, I'm saying I'm going till moments of degree M and approximation within epsilon. Can I take the K, the size of the matrices for the microstates, large, and so that it ensures that there exist microstates? So if I'm having approximation within epsilon and for moments up to degree M, can I find matrices which give this? And this is actually, that this would be non-empty is equivalent to the famous Kohn problem about embedding it to the into the ultra product of the hyperfinite to one factor. So we know that the answer is negative, so there exists such x1, xn for which this microstate spaces will be empty. So when you start taking logarithms of such things, you have logarithms of 0, so the volume is 0, so things break down when you go, or you can say it's minus infinity. Well, it's, so there is a connection at one limit to the Kohn problem at one limit, and it will come back in other questions. Now, you have many things in von Neumann algebras which have analogues in C-star algebras, and there is a rather big development of many things we know in von Neumann algebra, trying to find analogous things for C-star algebras. And for instance, for classical entropy, for dynamical entropy, there is a topological dynamical entropy for certain topological dynamics. And there is actually also such a topological free entropy. So it's a kind of free entropy in the C-star algebra framework. And here, instead of a von Neumann algebra, we're going to have an n-tuple of self-adjoint elements in a unital C-star algebra. So instead of M tau, I'm having just this A and with A1, AN self-adjoint elements in A. And I want the quantity, the topological free entropy. And this free entropy, this topological free entropy, is defined using norm microstates. So the microstates, I'm having not an expectation functional, and since I don't have an expectation functional, I will take norms of polynomials, norms, such things. And so the microstates now, instead of K is the size of the matrix, epsilon is the degree of approximation, but instead of looking at moments up to degree M, I'm having here polynomials, P1, PM, and P1, PM are non-commutative polynomials, and the microstates are self-adjoint K by K matrices, which satisfies the condition that the polynomials P1, PM, their norms, if I compute them in the microstate in C1, Cn, or in A1, AM, are within epsilon of each other. That's the condition. Now, you know, one is always tempted with the stories of operator spaces, and so to say, why stop at polynomials? Why not take matricial polynomials, matrices? But it's equivalent. So it's enough to look at this kind of microstates for polynomials if I don't gain anything by looking at matricial polynomials with coefficients matrices.
Why is this called topological? Why is it called topological free entropy? Why the word topological?
Well, I mean, because when you do this, something analogous for the Kolmogorov-Sinai entropy of dynamical systems, which is a von Neumann algebra setting because it's measurable, you get to topological dynamical systems, and it's called topological entropy. There is for dynamical entropies, there is a very good analogy. It's called topological. And besides, von Neumann algebras are measurable, C-star algebras are topology, but topological in the sense of general topology, not of algebraic topology. Yeah.
Can I ask a question? It's clear that if you take polynomials with matrix coefficients, but the dimension of the matrix coefficient is fixed, you get the same thing. But if I allow the dimension to diverge, would I still get?
Yeah, you get the same thing. It's such tricks that you transform evaluating certain norms from matrices. You can evaluate them if you get from polynomials.
Only if the dimension is fixed. But if I allow the dimension of the matrix coefficients to diverge, let's say I allow the dimension to be the same as the
finite number. You have a finite number of polynomials.
Ah, I see.
In a microstate. You don't have a sequence.
So there is no, there's nothing to be gained.
Yes.
Well, I mean, you could do the same with polynomials to insist that you get more and more with logic A. But
then you get a completely different story. Yeah, okay. Very good. Yeah.
Okay, so that's the topological free entropy. And then same game, limit superior, k minus 2 logarithm volume of the topological microstate plus n over 2 logarithm of k. And then you take the infimum epsilon positive, m over n, p1, pm. So you see instead of m moments up to degree m, because here you cannot take linear combinations of the moments, we need polynomials, p1, pm, non-commutative polynomials, and you get this topological free entropy. Now, if you look at what happens in dynamical systems, then the topological entropy is obtained as a maximum over entropies with respect to invariant states, invariant measures, stuff like that. So you have here something similar. You can, not that you have the result, but you can imagine a similar quantity, which I call the free capacity, this competing quantity. So I'm having AJ non-commutative, AJ self-adjoint elements in a C-star algebra with unit, and then I'm taking the free capacity of A1, AN, it's this thing here, K of A1, AN, and it is the supremum of the free entropies of A1, AN in the representations associated with tracial states of A. So you take tracial states of A. With a tracial state, you have a GNS representation. The GNS representation gives you, because it's a trace state, gives you a von Neumann algebra with a tracial state. And then you take the usual free entropy, and you take the supremum over all such trace states, and this is then the free capacity. Yeah, and it's a somehow competing quantity with topological free entropy. In case n equal 1, what do we have? In case n equal 1, you see it's you have one self-adjoint element. One self-adjoint element has a spectrum, so it's a compact subset of the real line. And then you take a maximum of minus logarithmic energies over probability measures supported on that compact subset. And this is what is called capacity in potential theory. So this is potential theoretic capacity. Of course, with a small change, I mean, it's that you take here an exponential instead of k of a. But up to this scaling using an exponential, it's the same idea for the logarithmic capacity, which plays an important role in potential theory. And the basic problem about this is whether the topological, this capacity k of A1, An is equal to the topological free entropy. And half of this can be proved. That it's true that the topological free entropy is less than or equal the free capacity. Yeah, that's a theorem, that the topological free entropy is less than or equal the free capacity. And you know also that in classical potential theory, you call the measures which maximize that, which extremals for this logarithmic energy, you call them equilibrium measures. So we can here talk about equilibrium, free equilibrium tracial states for the generators A1, An of C-star algebras, and these are the trace states for which this usual free entropy is maximized, and they are not necessarily unique. That's what's happening. It's not proved that they are unique. And here are some examples. Yes?
Can I ask a question? I mean, if we take, for example, the reduced C-star algebra of a free group, it has a unique trace.
Yes.
Is then the conjecture that the topological... Oh, okay. So, okay.
I'm going to discuss such example. So the universal, first example is the universal n-tuple of self-adjoint contractions. That goes into the full free products, like also the full C-star algebra of a free group is a quite related object. So the universal n-tuple of self-adjoint contractions, so it's a C-star algebra generated by T1, Tn, and it can be identified with the full free product of these C-star algebras of continuous functions on -1, 1. And if you take a trace, then you have the classical equilibrium measure on -1, 1, which is this arcsine law you see here, this pi -1. And if you take a measure which is the free product of this, then you get a free equilibrium trace state for T1, Tn. Yeah, so it comes here as a free product, but for arcsine laws. Then you have the semicircular case. The semicircular case is the case of having S1, Sn, the large n limit of independent, identically distributed self-adjoint Gaussian random matrices, n by n matrices, G1, Gn. The large n limit of this gives you the semicircular system. It's the same thing as n freely independent self-adjoint elements, which each one has a semicircle distribution. It's the same thing as the field operators, the left field operators on a full Fock space, yeah, with a vacuum expectation. All these give you semicircular systems. They are the analog of Gaussian elements in free probability. And then what we have in this case is that the topological free entropy of S1, Sn is equal to the free capacity of S1, Sn, and is equal to the free entropy of S1, Sn. So free entropy, microstates free entropy, topological free entropy, free capacity, all are the same in this case. And the essential ingredient is the Hagerup-Thorn-Bjørnsen theorem, which tells you that you have this type of strong convergence of the distribution of an n-tuple of Gaussian ID random matrices. So this means that you don't have only that, if you take a polynomial in G1k, Gnk, you don't have only that the traces, the normalized traces converge to the trace of the same polynomial in S1, Sn, but you have also almost surely that this convergence takes place also for the norms, and this is the notion about one of the early occurrences of what is strong convergence and of what you're going to hear a lot at this workshop. So the Hagerup-Thorn-Bjørnsen theorem is a key ingredient to prove some of these results. And since there has been so much progress on strong convergence, it is perhaps natural to ask a corresponding question about this equality between free capacity and topological free entropy. Namely, the fact that you have this equality for semicircular systems being the strong limits, if you want, or the limits, the large n limits of Gaussian ID matrices, it's perhaps natural to ask what happens if instead of Gaussian random matrices, you'll take this more general random matrix models, the large n limit of random matrix models. So instead, you see for the semicircular, the polynomial here is x1 squared plus x2 squared plus xn squared. If you want, here you have a more general exponential minus n trace. P is a polynomial with certain virtues. This is also the kind of states of things they read is also the subject of what's called free Gibbs states at present. So it's basically, can one, with the new techniques about strong convergence, will it be possible to have, besides the semicircular system, have also results for such equalities between free capacity and topological free entropy for free Gibbs states or things like that? It's been so much progress that maybe something can be done. Okay. I'd like to go back maybe to the first thing, this free product, so that we took the trace state space of such full free products. And I should say that there is also big progress recently, not that I'm sure it will be relevant to this question, but there is progress on understanding these trace state spaces for full free products of C-star algebras. I should mention work of Slutsky, Vigdorovich, Adrian Ioana, who have shown that such trace state spaces lead to pools and simplices and things like that. So there is also there some progress which can be, I don't know, it's much farther from the questions, but could serve. Now, the non-microstates or microstates free approach to free entropy, it's an infinitesimal approach. It's based on what is called free Fisher information. The free Fisher information is something which arises more or less like a derivative of entropy if you let your variables perform a Brownian motion. So something similar, since you have free Brownian motion, something similar can be done here. So that is how one could describe the classical and the new thing. So classically, you have a score function. So you have one variable. It has a distribution p dt on the real line. P is the density. Then you have in L2 of the space with respect to this density, you have d over dt, the differential operator, which gives rise to an unbounded operator. And this, the adjoint of the d over dt applied to 1, the square of its norm is the Fisher information. D over dt star applied to 1 is what is called the statistical score function. So it's the score function for this variable. And something similar can be done also for, can be also described using the derivative in another way. So it's derivative along the Brownian motion, you see it here, 2 times limit entropy h plus epsilon square root g, which are independent minus h. It's a derivative of. And the free analog of this is done by using in the analogy, instead of the usual derivative d over dt, using the free difference quotient. So we're passing from a derivative in a commutative setting to an entropy in a free setting, in a non-commutative setting. And then the free difference quotient is the following derivation. It is, so we're having here the non-commutative polynomials in one variable x with coefficients in a ring B, in a unit ring with unit. And we're having del xb from b of x into b of x tensor b of x. And oops, I shouldn't have written b of x 2 times. Yeah? So erase this b of x in the first arrow. So it goes from b of x to b of x tensor b of x. And it is the derivation which takes b, treats them as constants. So the derivation on b is 0. And the derivation on x is 1 tensor 1. And then the free conjugate variable, that's the analog or free score. It's the analog of the statistical score. It is taking the adjoint in L2 of M with respect to the trace of the vector 1 tensor 1. So you take 1 tensor 1, apply the adjoint. That's the analog of d over dt star applied to 1. And that's called the conjugate variable. And then the free Fisher information, it's defined analogously as one defines in classical statistics the Fisher information. Is this thing phi star of x1, xn is the sum of the traces of the expectation of the square of the scores, jk. And here, these scores are partial scores. You treat jk, you treat x1, xk minus 1, xk plus 1, xn as constants, and you treat xk as variable, and you take the corresponding Fisher, the corresponding score function, and get all this. Now, the formula for the free entropy defined with this Fisher, with these conjugate variables or Fisher informations, is done by a classical formula. It's absolutely the analog of such classical formula for differential entropy using score functions. And to have it here, chi star x1 xn is n over 2 log 2 pi e plus 1/2. And here you see x1 plus t square root s1 xn plus t square root sn. That's the x1 xn performing a Brownian motion. Yeah, if you s1 sn, the x's and the s's are semicircular and are freely independent of x1 xn. So distribution-wise, it is x1 xn are the starting point of a free Brownian motion. And then we're having, of course, the problem of unifying these notions. and seeing if they give the same thing. And that's a unification problem. Wherever chi is equal to chi star, and for n equal 1, it's true that chi of x is chi star of x. And there is also, in one direction, there is also, has been from early point, a general result, one inequality beyond Capitaine and Guionnet, so that the free entropy is less, the microstates free entropy is less than or equal the non-microstates or microstates free entropy, chi is less than or equal chi star. But you cannot expect actually to have equality in general. The full unification problem would imply a positive answer to Kohm's problem, because you can make out of xn, x1, xn, you make a semicircular perturbation, and to get something which would have non-microstates entropy, which is not infinity, and so you get you'd get existence of microstates if unification would hold, and this contradicts Kohn problem. So the unification problem cannot be true in full generality. And so what one can expect, maybe one should have more modest aims. Instead of this full unification problem, which we know has negative answer, one can go for a modest unification problem that is assuming we're having x1, xn being part of the von Neumann algebra of a free group. Now, von Neumann algebras of a free group, you can put one into any other one. Yeah? So you can put one with 2 generators into one with infinity generator, one with infinitely many generators into one with 2 generators. Doesn't matter. I've chosen to put here 2 generators, and it's the same thing as the von Neumann algebra of a semicircular system. So a modest unification problem would be whether the free entropy and the microstates free entropy and the non-microstates free entropy are the same for n tuples of self-adjoint elements in the von Neumann algebra of a free group. It would be still a very difficult problem, but at least we're getting past the Kohn problem difficulties. Now, the next thing is that there is a notion of free entropy dimension, which is defined in the following way. Delta x1, xn is a lim sup, and here you see what you do is you perturb x1, xn with a freely independent semicircular system, x1 plus epsilon x1, xn plus epsilon sn, and to divide by the logarithm of epsilon in absolute value. One would be tempted to use, instead of epsilon, use square root of epsilon to make it like a Brownian, free Brownian motion, but you can write it also with epsilon, so whichever you prefer. So S1 Sn is a semicircular system, freely independent of x1, xn, and it is this formula, delta x1, lim sup, epsilon goes down to this and have the free entropy. Yeah. And let's see what it means geometrically on microstate spaces. The microstates free entropy is the logarithm of the volume of a volume of microstate spaces, gamma, what you see here. This del, the free entropy dimension, is actually something is called the Minkowski content of the microstate spaces. Everything here is meant in an asymptotic way, but so one is a logarithm of volume and the other one is a Minkowski content. That's a basic idea. And there is a variant, del with index 0, where instead of using microstates for x1 plus epsilon s1, xn plus epsilon sn, you use them, so-called microstates, in the presence of s1, sn. So you use microstates which extend to microstates of x1 plus epsilon s1, and also to the s1, sn. So you have such systems of approximating matrices, which you can also find for the S's. But that's a technical matter, but it appears all the time with del n versus del 0. And what's remarkable is that there is an equivalent definition of this del naught of x1, xn, of this free entropy dimension, using packing dimension. So you use a number of elements, maximal number of elements which are within epsilon distance in a certain metric state. So any two are within, maximum number of elements, so that any two would be a distance at least epsilon of this. And Kenley-Jung has such a geometric definition. So it's another way of, it's very valuable to view microstate spaces in this geometric way. And since I've given also for the entropies, let me tell you what the microstates free entropy dimension is for one variable. Basically what you do, you take, so variable is an element in the von Neumann algebra with a trace state, and then you look at the atoms of the spectral measure. And the traces of the atoms of the spectral measure, these are the mu of t, and you square them. So you take 1 minus the traces of the atoms squared, and that's the free entropy dimension. And you have the free entropy dimension problem. The free entropy dimension problem is the following. I mean, say I have a von Neumann algebra with a trace state. Say I have two generators, x1, xn, and y1, ym. And the question is, does it imply that the free entropy dimensions are the same? So if it would be the same, then the free entropy dimension would become an invariant of the von Neumann algebra. You take the von Neumann algebra, you take any generator of the von Neumann algebra and its free entropy dimension, you get the same number. So the number depends only on the von Neumann algebra. If you can prove something like that, then you are lucky because you've solved the non-isomorphism problem for the free group factors. So we are not yet there. That's, so you would know that if M is different from N, the free group factor on M generators is non-isomorphic to the free group factor on Fn generators. And the whole problem is actually, you see, is that when you take generators, you take the star algebras generated by x1, xn, and by y1, ym, and then you take a closure. The closure produces a headache. I mean, as long as you would take only you would take algebras generated, then you'd get the same thing. So the free entropy dimension is known to be an invariant of the algebras, x1, xn, but not of the von Neumann algebras, not von Neumann algebras, C-star algebras. You cannot go beyond closure. That's what we know at present. Yeah. And there is a remarkable special situation that of strong one-boundedness discovered by Kenley-Jung. And what he discovered is that if you are very close to free entropy dimension 1, then, so below 1, so there is something which, a quantity which is invariant also if you take these weak closures. So if you look at what it means, the definition is this. You take such a von Neumann algebra and you take an n-tuple x1, xn, you call it strong one-bounded. If you have, if you have this, that you make this semicircular perturbation, and then the free entropy is less than or equal n minus 1 logarithm of epsilon plus c, yeah, plus a constant. Now, if instead of c, of the constant c, you'd put a capital O of log epsilon, then you'd be just dealing with a free entropy dimension. But since you've put this constant there, it's a much more restrictive notion. And Ken Lee Jung discovered this notion inspired by certain things about fractal sets. He read books about fractal sets, stuff due to Besikovich, and came up with this ideal. And then you have, for strong one-boundedness, you have the following thing which shows that it is preserved when you generate, but there are still some restrictions. So if you have x1, xn strongly one-bounded, and one of the, say the first, of x1, xn has finite free entropy, then the von Neumann algebras of x1, xn and of y1, ym are equal, then also the von y1, ym is strongly one-bounded. So this is a property which goes through if you take the generated von Neumann algebra. And you have this condition here, this condition that the free entropy is finite. And this has been further developed. There is work of Ben Hayes, which has gone much farther about that, and namely, things instead of finite free entropy, you have von Neumann algebras of various parts of elements being hyperfinite, other conditions. I cannot go into this. Now, another, you may wonder, what is, so we know the microstates free or non-microstates free entropy is one way of looking at this is that it is a kind of Minkowski content versus logarithm of volumes. Now, there is another way to look at this. And what one does is now, but we look at this, this microstates free entropy dimension in the microstates free setting. So we're using this translation. We're going over from, we're going, where is this? We're going from chi to chi star, and this gives del goes to del star. And then we're having that del star, if x1, xn is a generator, you see here is not the von Neumann algebra of a group. It is a group ring, the algebraic ring. That's only algebra, no limits of a discrete group. It's a subring of the von Neumann algebra. Then del star x1, xn is this combination of L2 Bethe numbers. And this you can find in, so there are the papers of Kohn and Dima, Mineev and Dima, and you can find these things. And there is another thing there, which is another notion. There is this, so here you have this del with this type of asterisk, and there's another notion there, which is a del with another asterisk, which is easily confused with this, so better draw a flower. So if you want to make the distinction. And this other one is n minus something like that, lim inf or whatever, epsilon phi star of x1 plus square root, d minus square root or without square root epsilon s1, Sn, and this is slightly larger, and in a number of problems, it's better suited than the simple analog. And you also have the same equality for C of G. Now, there is another thing I'd like to mention in all this, and something which has to be taken with a grain of salt, because the technical difficulties are very, very serious, and the results are very partial, but somehow it's an important connection. It's a connection which has to do with these free Gibbs states, with other things around entropy, and so even though I would not look at it as technically very, something which one can deal easily, but I think conceptually I have to mention it. The variational problem for chi of x1, xn, and it's the connection with the large n limit of random matrix models. But again, please be aware it is cum grano salis, with a grain of salt. So we're looking at the variational problem chi of x1, xn minus tracial state of a polynomial of x1, xn, p a non-commutative polynomial. And then what one can conceive something which would be like the critical point condition for this variational problem. And the critical point conditions have something to do with conditions which appear also when one looks at the large n limit of these random multi-matrix models. Remember, they appeared also in a question about, I mentioned about topological free entropy. I won't say more than that because that's shaky ground. Well, there are results, particular cases, but conceptually it's a very important thing connected to free entropy. Other things I'd like to mention, where I won't have time to go into this, is now you see the free Fisher information, all these things, they depend on this free difference quotient derivation, this del. And there is work to go beyond the tracial setting. There is work by Dima and by Brent and other people associated with them. And, but it's a subject which has a much further development. It goes beyond the type 2-1 setting. It goes to type 3 and other things which I have not gone here and said anything. The other thing I would like to mention is that there is work on strengthening the unification question. There is work that the unification question has a probabilistic way of a stronger probabilistic problem, which is a large deviation problem for random matrices. And I should mention especially the work of Alice Guionnet and her co-worker. There is many results in this direction. In any case, this goes beyond the unification. It is stronger than unification, but of course, the results are partial. So I have here a number of references. I have a survey paper with free entropy in the Bulletin of the London Math Society from 2002, which covers many things. You see, I talked very little, I said almost nothing about the properties of these free entropy quantities. Some of it are listed there in this survey. The survey has just at some point flow. There are a few lines on a certain page about a semi-continuity problem, and that is wrong. There is a semi-continuity problem somewhere, just a few lines. Dima found early on a counterexample that this semi-continuity problem, but otherwise the rest is safe ground. Then there is this old paper of mine, Topological version of free entropy, where you can find also other things about the topological version. You can find also stuff about topological free entropy dimension and about topological free entropy dimension. There is also further work by Don Hadwin and Junshao Shen, and so that's for the topological. Then there is the Kenley Jung work on, I've given here to you the reference to the strongly one-bounded von Neumann algebra paper. Then there is a big paper on one-bounded entropy and regularity problems on von Neumann algebra of Ben Hayes. And I've put also here the two papers of Dima and Alain Cohn and Minev. And to get through now there are, with the computers, it's easy if you have a few references to get to other ones. Yeah, you know one paper and you look where it's been cited and what it cites, and you get to other references. And so this is what thanks for listening.